Now let's look at differentiation. What we want to know is, if we were to differentiate a function in the time domain, what happens to that function in the frequency domain? Equivalently, if we were to differentiate the function in the frequency domain, what would happen to the function in the time domain? So let's start off by looking at the inverse transform. So I've got the inverse transform here. We're going from the frequency domain, a function f of I omega, to the time domain, which is a function f of t. Now if we were to differentiate this side here, which is the d by dt of our function f of t, we would have to differentiate this side here as well. Now the only factor here that is a function of t is this e to the minus I omega t. So that's the only part of this that we need to differentiate. Now the I omega just acts like a constant, so that's going to give us I omega times e to the I omega t. So we're just left with this function here. So what we can say is, whenever we differentiate a function with respect to time, what we're left with is a factor of I omega, so this is the factor I omega here, and what we've got left over is 1 upon 2 pi the integral from minus infinity to infinity of f of I omega e to the I omega t by d omega, which is just the Fourier transform of our function f of t. So what we're left with then is if we were to differentiate a function in the time domain, it's equivalent to taking the function f of I omega in the frequency domain and multiplying it by a value of I omega. So that's one of the transform pairs that we're interested in from this video. So now if we were to take the nth derivative with respect to time, we would just continually differentiate this, so we would get I omega squared, cubed, and so on and so forth. So we would just get I omega to the power of n times f of I omega. So this is our second little transform pair. Now we can do the same thing the other way around about. We can look at the forward transform. So we're going from a function of time to a function of frequency. And then we differentiate the function of frequency with respect to omega. So that means we have to differentiate this side as well. Now the only thing here is a function of omega, again, is the e to the minus I omega t. So whenever we differentiate that, the factor of minus it just looks like a constant. So we just end up with the f of t, and there's a negative sign there as well, so it's negative it times e to the minus I omega t by dt. So again, what we can say is that when we differentiate the function with respect to frequency, we're just going to be left with the minus it, and what's left over here is just the Fourier transform of the function, which gives us a function f of t. So when we differentiate a function with respect to frequency in the frequency domain and the time domain, it's equivalent to having the original function multiplied by a factor of minus it. Now the same thing applies here as above. Whenever we look at the nth derivative, in this case here we get minus it to the power of n times our function f of t. So these are our four little transform pairs here. Now we'll go and we'll look at them graphically, and then we'll go and we'll put them into the MATLAB, and we'll see it done in MATLAB as well. So here's a graphical interpretation. Let's imagine we had a small triangular function like this here. Now when we find the Fourier transform of that triangular function, we get this raised sinc function. So also everything's above the in the positive axis here. So you can see this as a little function. I'll show you this in MATLAB just in a minute so you can get a better picture of it. Now whenever we differentiate this function here, we get the little square function. So you can see that there, the rate of change is a constant positive value, so here's a constant positive value, and the rate of change is a constant negative value, so that's a constant negative value here. So this is the function of time, and this is the derivative of that function. So when we said that we differentiated a function in the time domain, it's equivalent to multiplying the function by I omega in the frequency domain. So let's go ahead and we'll multiply this function by, first of all, omega. So omega is just the value of this axis here. So it means that you can see as omega tends towards 0, the whole thing's got to tend towards 0, and it will raise up in this manner. Okay, and everything else along here is just going to be a scaled version of this side of the function here, and of course the other side as well is going to be multiplied by minus omega. So what we see here is a 0 at this point, and then everything else is below the I omega axis. We then take this function of omega fi omega and we multiply it by I. Now if we multiply by I, it's equivalent to a rotation of 90 degrees. So we rotate from the purely real axis onto the purely imaginary axis, and this rotates one direction and this one rotates the other direction. Okay, so if everything works out well, right, then when we Fourier transform this function here, it should give us this function here. So let's go and have a look at that in MATLAB. So this is one of the plots from MATLAB. We have our triangular function here, f of t, and when we find the Fourier transform of this triangular function, we get this raised sinc function, and it's a purely real function of time, of frequency. There's no imaginary parts here. So let's go and we'll differentiate this, and we'll see what happens to the function in the frequency domain. So this is a function here being differentiated. So the triangular wave gives us this little square pulse, and whenever we find the Fourier transform of that, we get this function here, which is what we've seen in the previous slide. And you can see this is a purely imaginary function. There's no real part to it. So let's go ahead and we'll just produce this in MATLAB, and I'll show you the little equations to produce it. So all of the equations that we're going to put in here are in the resources section, so you can get in there and just copy and paste them. So let's first of all, we'll find our triangular function. So whenever we produce the Fourier transform of this triangular function, as we've seen in a previous video, we get this purely real function here, which is our raised sinc. Now what we're going to do is we're going to differentiate this triangular function and then have a look at the Fourier transform of the differentiated function. So in order to differentiate it, first of all we have to tell it that the value of t there actually exists. So we'll put in sy ms t, and then we can go up and we can do the differentiation of that triangular pulse. So there's the equation there for differentiation to the right. So you differentiate this function, and when you work through the differentiation, it gives you this new function here. So then we're going to take this new function and we're going to find the Fourier transform of that new function. So we'll put the new function into the Fourier transform. So we're going to Fourier transform this new function here. And we'll see that our output here is, well, our input is going to be this little function here, which is the triangular wave which has been differentiated, and the output here is what we had seen previously in the previous slide. So it's a purely imaginary function, and it's purely odd as well. So that's all there is for this video. I'll get you on the next video. Goodbye.